Professor.
Good evening to all. Welcome to Energy Material Research and Fund. Today with us, Dr. Sujay Bandhopadhyay and Dr. Subhrajyoti Bhandary. So, Dr. Subhrajyoti Bhandary, he is a young dynamic researcher. He has published 53 reputed journals, among which he recently published JACS, Journal of American Chemical Society. He has also published in Angochem, SS Nano, Nano Letter. Today we will now from him so about the important factors he will share with us based on his experience. What are the important factors new researchers can follow to publish in a good article? So, based on his research area, he will share with us. So, really, it is our immense pleasure to invite Dr. Subhrajyoti Bhandary from Ghent University.
Thank you, Arpan, for the introduction. So normally, I would say I am a young researcher in this field. I am working in the broad area of chemical crystallography and material science. So in this area, basically now, crystallography is more or less inclined towards the material science. You will see a lot of, collaboration between crystallography and material science nowadays, and that field is also rising, particularly the flexible crystals or dynamic crystals. Normally, these materials are stimuli responsive materials. You can apply any kind of stimuli like heat, pressure, or magnetic field, or force, or light, and you will get different kind of dynamic responses, like it can jump, it can break. Crystal can break, crystal can jump, or any kind of this dynamic responses. These materials are very useful in different devices like artificial muscles, energy storage devices. So that's the reason this field is growing, or rapidly growing, I would say, and it has very promising application in making different kind of devices. So I'm focusing in this kind of research here at Ghent University, although I'm chemical crystallographer by training. And another thing I would add here, this kind of materials which have luminescence property, particularly fluorescence or phosphorescence, those are very emerging, field nowadays. So yeah, but the problem is in this field, the design principle. Since this field is emerging, so far there is no such principle that you will follow this kind of guidance or this kind of methodology, and you will get this kind of phenomena or features. So these are highly unpredictable. But yeah, with few strategies or methodologies, you can synthesize this kind of molecule, but the stimuli responsiveness depends upon many factors. And another thing is that although these materials are highly crystalline, but due to this dynamic effect, such materials often loses their crystallinity. So yeah, this is a challenge for researcher to make such kind of crystalline materials. Yeah.
Bhandary. So I think the phosphorescence or fluorescence luminescence materials become very interesting because it's a decay time. It's long time phosphorescence, long time decay. So for this reason, phosphorescence become more popular. And recently, that the topic is room temperature phosphorescence materials. Getting a room temperature phosphorescence materials is quite interesting compared to fluorescence materials. And we know the principle generally that if there is any conjugated materials, high long conjugation present, and also planar geometry, then it's give the fluorescence very easily. But the when singlet to triplet jump is occurring, that time we are getting phosphorescence, right? So what is the designing principle to get a molecule to who can do the phosphorescence, and particularly room temperature phosphorescence? If you discuss that thing, I think it's quite interesting for as a research topic.
Yeah, so room temperature phosphorescing is also now very interesting field, as Sujay said. I like room temperature phosphorescence is known for metal containing compound like transition metal, their transition, but room temperature phosphorescence in organic molecule, which normally only contain carbon, nitrogen, or other halogens. For the organic molecule, the design of room temperature phosphorescence is very challenging. But yeah,
Yes,
there are few reports nowadays, few design principles also, like in crystalline materials, like it's called the aggregation induced emission. I mean, in aggregated states, you will get normally room temperature phosphorescence in organic molecules or organic compounds, better to
okay.
say. So
And also
now,
if it is coordinate with metal, means transition metal, means like metal ligand chelating complex, I think that is become more long time decay time, right? Means that singlet
yeah,
to triplet
when
jump.
any kind of transition metal is there, so due to the spin orbit coupling, it's more feasible to do spin orbit coupling having transition metals in the compound or materials. So it favor room temperature phosphorescence. But in organic materials, normally spin orbit coupling is very, very less. So, but yeah, there are few factors in the supramolecular level. Those factors play a very important role in showing room temperature phosphorescence in organic molecule, organic materials. So, like if you have very strong intermolecular interactions that can rigidify the motions in the crystals. Although we know the crystal is a rigid, entity, but in
Yes,
crystalline environment also molecules are in motion, some kind of motion. So those
okay.
motions normally favors radiative decay process, but due to presence of very strong intermolecular interaction in the crystal, like strong hydrogen bond or any kind of halogen, particularly the halogen, if halogen atoms are present, like heavier halogen, like bromine, iodine, those halogens can produce or show room temperature phosphorescence by enhancing the spin orbit coupling. And
Yes,
halogen has halogen atom can form very strong halogen bond that also help in room temperature phosphorescence for purely organic molecule.
yes. Yeah, halogen moiety is needed, means to get a room temperature phosphorescence, because I think they have very high molecular orbital, so that can help that the spin orbital rule relaxation, means that for this reason that singlet to triplet jump is happening. So if in molecule, in organic molecule, if we have some halogen moiety, then it will be helpful for phosphorescence. And also that which kind of, and also helping for packing, like whatever that in spectroscopy during aggregated state, I think packing is very important. So in hydrogen halogen halogen bonding interaction is very good. So you have lot of experience in crystallography, so can you share which halogen bonding interaction is better? Fluorine, bromine, chlorine, iodine, which have lot of halogen compound, so which halogen moiety we choose for getting a good packing or good interaction?
So normally heavier halogen, as I said, heavier halogen, bromine and iodine, those halogen has sigma hole. Like
Yes,
if
yes.
this sigma hole is generated the opposite direction of the covalent, like if bromine is attached to any carbon, so this C in the opposite direction of C Br bond, there is electron deficient region called
Okay.
sigma hole. So this sigma hole can interact with electron donating species in your molecule. Like
Mm-hmm.
if you have like CO kind of moiety in your molecule. So these halogen sigma hole can interact with oxygen lone pairs in CO, and this interaction is electrostatically very favorable or electrostatically stabilized. So automatically it is stable interaction and attractive interactions, and that kind of interaction packed the molecules in the inside the crystal lattice very, I mean, well fashioned or very good fashion. So the overall this intermolecular motions is reduced, and it can show the room temperature phosphoration.
Quite interesting. Means you have discussed very excellent designing principle. So I think it will be very helpful for whoever the new
Working in this
researcher
area,
particularly.
yes. And for this, like the quality articles, generally, what are the basic factors new researchers should follow from the beginning itself, so that they can also try to attempt in this good art to publish in good articles. So, in your experience, what you can say to the new researchers that they should follow at least these points, they should work on that for the new researchers
Yeah,
to
so
publish in a
in
good
this
article.
area, although I don't have very experience, I am also new researcher in this area. So, but basically, you have to look into the gap in this area. Which are the gap which I can contribute something in that gap, so that like in the initially I said the combination between or collaboration between this luminescence field, particularly room temperature phosphorescence field and crystallography. This is a very interesting area. You can do a lot of, I mean, there are a lot of space or scope in this area nowadays, because normally the luminescence people are involved in this luminescence study, and crystallographer are doing different thing. But if you combine these two area, so you can design lot of new materials with promising
Sentence.
properties.
Hello. So
Yeah.
here I would like to one sentence in these things that as already you have discussed that people are moving to crystallographer and moving to material science fields or like that, means it's interesting. So now the world is look like that. It's not a competition thing. We should this time is do collaboration, good collaboration with impact.
Yeah, indeed. I mean, although in the
Bhandari said that
collaboration in crystallography and material science is long, I mean, known for a long
you
time.
feel that then it will be also will highly impact your journal or
But
your work will be affected.
as I said, to design this kind of crystalline materials to get good metal-free room temperature phosphorescence compound, you need very good knowledge of supramolecular interaction or intermolecular interaction and crystallography, because everything happening in crystalline environment, aggregation or crystallization induced emission basically. So if you have very good knowledge of intermolecular interaction and crystallography, you can design these materials. Like I said, if you have halogen, I mean, you have to know, if you are incorporating halogen in your materials, you have to know, okay, my halogen can't form halogen bond. But to form halogen bond, you need some kind of electron donating species also. Yeah, halogen can interact, halogen sigma hole can interact with another halogen, lone pair of another halogen, and form the halogen bond. That is also very stable. But if halogen is interacting with this kind of CO like carbonyl moiety, so you have this pi hole kind of thing in also in CO.
Okay.
So your normally this N to pi star kind of, I mean,
Transition.
interaction, yeah, transition will enhance for this because of this kind of interaction. And halogen is interacting with carbonyl. If halogen is
Okay.
interacting with halogen, that will not, I mean, enhance the N to pi star transition to, I mean, which is favorable for room temperature phosphorescence.
here also, what halogen we should choose, fluorine or bromine
No,
or
no, no, no.
iodine? Means which halogen we
Fluorine
use?
hardly form, I mean, halogen bond. And if
Okay, okay.
sometimes
So hydro.
sometimes in different chemical environment, it can form true halogen bond, but that,
Mhm.
I mean, attractive interaction, I mean, that kind of stabilization is very less when bromine or iodine is forming halogen bond, because bromine and iodine has large polarizable electron density. It can interact strongly with other atom or molecule.
Okay. And also, Bhandari, I have one question that how you get, means what is the experiment you have performed to get a room temperature phosphorescence? Means what is the experimental technique you have followed? Means you have to just illuminate your materials and then keep it in dark, or what is experiment you have performed to get a room temperature phosphorescence?
I mean, normally we study. Anyone can study their luminescence spectra first, absorption or emission spectra. Then see the main factor is decay time. If you have room temperature phosphorescence, that
Hmm.
decay time will be very high, and once you decrease the temperature, the decay time will increase.
Yes, yes.
But in fluorescence, the decay time is like nanosecond scale.
Okay. Yes,
But
yes. In nano.
for phosphorescence, it's
Recently, as a main author, as a you published in JACS. So in that work, can you just share your experience on that work? If what exactly new insights in that particular in that work? Uh,
yeah. So maybe I can show the
has,
paper or
sure, sure,
what.
sure,
I
sure,
think it
sure. You
will be
can, you share,
nice.
yes, sure, sure. That will be great for us.
Just give me 1 minute to download it. I think I have to do share screen, right?
Yes, yes.
Ah, that arrow, you can just click it. You can share
I
your
think
screen.
now you can see the
Uh,
interface of.
yeah. We can see it. Yes.
So here it is also, I mean, room temperature phosphorescence molecular crystal, organoboron based, without any metal, and including 2+2 cycloaddition reaction in crystalline state. So we have design, I mean, we are working on mainly organoboron based compound to get efficient room temperature phosphorescence. And these crystals or these materials were synthesized via mechanochemical procedure. So no solvent or reagent are used to
I
synthesize these materials.
think that is a green approach, right?
That is
Green
green
synthesis.
approach.
Oh, green approach means
Yeah.
green in the sense like no acid and base or no that no acid or these things are no hazardous chemicals
No,
or
no, no. This is not routine, I mean, covalent synthesis. Like, so you need
Yes.
solvent, reagent. You just take the materials and grind them. You can grind manually, or you have different kind of instrument for grinding.
oh, okay, very simple.
So without any solvent,
Okay.
solid state synthesis, you can say. Yeah. So this is the molecular structure of this organoboron based materials. You can see this organoboron moiety.
Mhm.
Maybe I can, yeah. So this, can you see my
Yeah.
cursor or not?
Yes. We can
Yes.
able to see it. Yes.
So this organoboron triphenyl boroxine moiety connected with a linker like this phenyl bipyridine kind of thing attached to a CC double bond here. So these materials is room temperature phosphorescence, and also if you apply UV light, these materials can respond to the light and
Oh,
take different kind of shape.
okay.
You can see this
Yes,
is
yes,
bending
yes.
upon application of UV light from this direction. Then if you will like remove the light, then slowly it will get the initial straight shape here.
Oh, yes.
It is more, yeah, it is more clear in this case. Like here, this is one straight crystal. Now if you apply UV from the top direction, like then it I mean bifurcated like this, divided in two crystal, you can
Again, two.
see,
Yes,
you
yes,
can see.
yes.
Then once you slowly remove the light, then it will again not fully recovered, but some kind shape is some sort of recovered here, the straight
Yes,
shape.
yes, yes.
Or maybe I can show the video also, that will be more clear, I think, then how it's happening.
Yeah, so will be much more better in that
Yeah.
crystal bending.
Can you see or not?
Yes, yes.
Yeah, it is open,
So now it is
but
opening.
it is in black.
I think it will open soon.
Yeah. So anyone can also check the video from that. That is the beauty of ACS paper. If you look at in supporting, they have also mentioned the video also how that crystal bending is happening. So it's really stimuli responsive materials. By applying stimuli means by applying light, you can
Yeah.
respond your materials. So that's it. That's why it's called stimuli responsive materials. Whatever he started his talk, that stimuli responsive materials is interesting. So we have seen in that paper that when applying some UV light, we are getting the response, that bending thing is happening.
Yeah, there are different kind of response. Like you can see here in this case, can you see the
Sorry. So this is the crystal packing, I think.
yeah, this is
So
packing view.
packing view, right? Your molecule.
Yeah.
It's quite cool. Yeah.
So
Also,
again, like this is, I can show you the luminescence part. So you
Yes,
can
we
see
can able to see this.
yeah,
The
this emission spectra. So this is red spectra for pristine crystals. One we irradiate with UV, then the intensity is, I mean, quite enhanced.
yes.
You can see the intensity is enhanced. So this is happening because the solid state reaction is 2 plus 2 cycloaddition. This is the initial crystal. Then after UV radiation, it formed this kind of cyclobutane ring. Can you
oh,
see?
that is that in situ it is generating that cyclobutane ring. So that's why
Yes.
this thing it's quite interesting. Quite interesting. Excellent result.
So then once you dissolve these, I mean crystals, this cyclized crystal 2 plus 2, photocyclized crystal, then it will form supramolecular polymer.
Oh,
And all those crystals and material, these molecules, these materials are room temperature phosphorescent, not the initial one.
okay, okay. So this is the stimuli responsive. Means
Yes.
applying light, there is some changing is happening. That cyclobutane ring is forming. So that's why
Yeah.
it's called steam.
If you apply light, that change is happening both in supramolecular level, like it is going to a topochemical reaction, single crystal to single crystal, and also their luminescence or phosphorescence property is also changing. I mean, you can see the intensity is increasing, so you
Yes.
can use these materials as a, detection purpose or sensor, optical sensor.
Optical sensor.
Yeah.
Quite interesting work, and it's really beautiful work.
So yeah,
As a
this is
enjoy this kind of
also
good work.
And the graphical abstract, which you can see that one, so that one draw using PowerPoint or no, some the very
these
beautiful
are
image in the graphical abstract. A graphical abstract I can see very beautifully in the abstract.
this one, right?
Yes, yes, yes.
Yeah, this is I think, yeah, PowerPoint, I think. I'm not sure, maybe I forgot. I think PowerPoint. The graphical abstract, yeah.
Okay, sir.
Thank you very much for sharing with us about your research work. Thank you very much. So really it will be very
Thank
helpful
you.
for the new researchers.
Thank you for inviting me.
Yeah, thank you, Subhrajyoti. So it's a very good work, and we hope we are expecting also many more good work coming from you.
Yes, so really we are proud that like you are working also like publishing very good articles, and also like in all the best for your future work. So and hope you will come back soon to India with a
I
very
hope
good
so.
position.
Okay, thank you.
Okay,
Thank you
thank you
very
very
much.
much. Thank you
Bye.
very much.
Thank you.